Hey everybody, welcome back to Organic Chemistry. Now we're doing Section 2 Aromatic Systems Part 1. And in this video we're going to go over more about the orbital description of aromaticity. Okay, and as always we're going to use benzene as our reference, but we know this can apply to many different aromatic systems. Okay? Alright, now the first thing I want to point out is we're going to talk about benzene here, the general chart of an orbital of benzene. Then we'll learn something known as the polygon or the frost circle model. We'll talk about the SHMO or the simple Huckel molecular orbital calculation. We're not going to go into much about that at all, but I do want to give you a quick visual representation of what it's all about. Finally, we'll do a quick summary of what aromaticity means from the point of view of orbital. Okay, from an orbital point of view. Alright, let's get started. So the first thing is a chart about benzene. Now, before we get there, I have to emphasize that you must know your basic philosophy from your conjugated chapter. Okay, so you must review the conjugated chapter about orbitals. Okay, because I'm not going to go into all that detail that I already did back then. So this is really a continuation of that chapter. So it's important that you have all that down. Okay? Alright. Now, if you remember, the first thing I want to point out is that if we have, let's say, a conjugated system, let's say we have an, not even a conjugated system, let's say we have ethene. Well, we were told that when you have an ethene, what it really is it's two p orbitals that come together, and it's either they're both shaded or they're opposite shades, right? So the phases are on the opposite side, and that's what creates a node. So this would be psi 1 and this is psi 2, right? And remember that electrons would be put into psi 1. This is increasing in energy. So this is all just a review. Now, so here's ethene, and this is its orbital description. We've got a node in between these two. And as you increase, if we had more than just one double bond, but if we had a 3 pi system and a 4 pi system and a 5, as you keep going up, the number of pi system, right, the number of atoms involved is how many times you go up and how many times you go across, right? This is all the stuff that we reviewed. This is from the conjugated system. Well, it turns out that one of the things about aromatics, aromatic systems have a larger homo-LUMO gap. Okay, that is a key characteristic. So a key characteristic is right here. So this is what makes it very special. So for example, if I have a hexatriene, right? This is a hexatriene. And I compare that to a benzene, okay, compared to benzene, which in a sense is like a hexatriene, but it's a cyclohexatriene, right? This is benzene. Well, we know that we're going to go, if I ask you, what is the pi system here? This is a 6 pi system, right? And the same here, 6 pi system. Meaning there are 6 atoms involved in this conjugated system. Same thing here. Well, if I was to go up 6 times, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, well, here's what we're going to find. Right, so this is psi 1, and 2, and 3, and 4, and 5, and 6. Well, what we would find, and I'm not going to go across 6 times with the orbital shape, it'll take too long to draw that out, but what we find is that when we fill in electrons, remember, we always go low to high, so this is increasing energy, right? And so if we have 1, 2, 3, 4, 5, 6, well, here's the thing. The HOMO, which is 3, right, that has electrons in it. That's psi 3 has electrons in it, highest in energy, highest occupied molecular orbital. And the LUMO is right above it, right? Psi 4 is the LUMO. There's no electrons. It's the lowest orbital with no electrons in it, lowest in energy, right? Well, turns out that the gap between here, like if I was to try to illustrate this for you right now, I would show it to you like this. I would say that, okay, This is it right here. This is the HOMO-LUMO gap. Now, the few things to point out. If I look at a 6-pi system of an aromatic system, the first thing that you're going to note is that actually some of these orbitals are the same in energy. So some of these orbitals are the same in energy. Now, what do I mean? Well, notice that, again, if this is going in increase energy, going up this way, first off, here is where we put electrons down below. 1, 2. But now look right here. 3, 4, 5, 6. Notice that these two right here are equal in energy. See, you don't get that with a non-aromatic system. So if you have a system that is aliphatic, an aliphatic system versus aromatic, an aliphatic system does not have degenerate orbitals. Remember the term degenerate? That means that you have orbitals that are equal in energy. It turns out that aliphatic straight chain systems, they go straight up. None of these orbitals are the same in energy. Whereas with an aromatic, you always have this configuration. You're going to have orbitals that are the same in energy. Now, here's the HOMO, and here's the LUMO. So this gap here is going to be much more extreme. So for me to emphasize that, I'm going to bring all this down. So the HOMO-LUMO gap here is much greater than if it's aliphatic. So that's the first thing. Aromatic systems have a larger HOMO-LUMO gap. It would take more energy to get these electrons to go up into the LUMO compared to these electrons here to go up into that LUMO. That's the first thing. And the second thing actually that we're seeing here is that aromatic systems have degenerate orbitals. And that's not something that we've talked about up until now. Now remember, a degenerate orbital, okay, degenerate orbital are equal energy orbitals. That's what it means, okay? And that's, you only have that if it's an aromatic system. All right. And by the way, in comparison to conjugated system, okay? Aliphatic conjugated. So straight chain conjugated, no degenerate orbitals. All right. So that's the second thing I want to point out. Now, another thing that we're going to say is that now, if we wanted to, let's say, another bullet point is if we wanted to measure the resonance energy, we will find that aromatic systems have more resonance energy than conjugated non-aromatics. Well, let's just write aliphatics. Conjugated aliphatics. Okay? So that's very important. So the aromatic system has what we call, it has more beta energy. Now, so that's aromatic. Aromatic has more beta energy. Now, what is beta energy? Beta energy is equal to the resonance energy. Okay, it's just a measurement that we use. That is the beta energy. Alpha energy is equal to just the energy of a p orbital by itself. So when you think about alpha energy, you're just thinking about the energy associated with a p orbital. But when you take two p orbitals and bring them together and then another two, and you start making conjugation, you get beta energy. You get savings. Energy savings. We call it beta energy. Okay? So aromatic systems have more beta energy or resonance energy. Remember, resonance energy is not a bad thing. The more, the better, meaning it's more stable. That's the case. So these are orbital characteristics that we need to consider. And now I'm going to show you the chart of benzene. Okay, so again, I kind of gave you a quick reminder, and I'm showing you the key identifiers about a comparison between aliphatic and aromatic. Now, here's benzene. Now, I want to point out a few things. Number one, this is increasing in energy. Now, do you remember that back in when we did this conjugated system chapter, we said that as you go up in